Alright, yeah, week 3, Thursday. Did I say week 8? Thought it was Thursday, week 8. Getting ahead of myself. So there'll be a quiz next week. The quiz marks are up already. Let me see if I can quickly show you. Would have to be the old one, wouldn't it? That's 2014. Clearly not what I want. This one. Alright, so if you log into the website, right down the bottom here you should find something like that. You click on that, it'll tell you what your marks are. I wonder what I've got. Possibly none. None. Oh, how sad. Hey, wait a minute, that's supposed to have quiz as well. Alright, I'll fix that. I must have fixed it for the undergrad course. But yeah, so that's where you find your grades. If you want to write a blog, that's how you do it. If you don't, well, that's fine. Alright, so assignment 1, we're still working on it. It'll be due at the end of week 6. And since there are no lectures in week 5, because I'm away, that will give you plenty of time to work on assignment 1. What is this crap? Yeah. Ignore that. I think that's left over from the previous version of the slide. How silly. Right, that's the one to worry about. If that was true, then you're all extremely late with your submissions. Consultations. Oh, I thought I removed all the old garbage from the slide. That's wrong too. Ignore that. We all know consultations are Monday 2 to 3, Wednesday 11 to 12. Alright, so that's what we're talking about today, probably. And that's what we'll talk about in the future. Right, so here's another nerd. Any guesses, and don't say Gandalf or Dumbledore, because it's not. Is there any clues? Can we see anything? There's probably some databasey type diagrams there, but this, once again, going back to this same guy in his younger days. Yeah, going back to the System R project again. So like I said last time, it was the original relational database prototype. There was actually, at the same time, or around the same time, Ingress was also implemented by Michael Stonebreaker. But IBM is obviously going to get more clout when they come to distribute it. So, System R, the original prototype, and a lot of the stuff I'm talking about was actually invented for System R. So, last time we talked about the buffer pool. Bruce Lindsay did the buffer pool for System R. And we'll see, there was a query optimizer, SQL, was designed for this system. But since that work on System R, he's gone on to work on a whole bunch of other stuff. And he works at the IBM Almaden lab, which I was fortunate enough to spend 6 months at in 1998. And I in fact gave a seminar that he attended, and we had a nice little argument about some aspect of the work. So that's good. Not sure who won. I thought I won, but who knows. Let's see. Alright, so we talked about pages. Let's get on to tuples. So that's the structure of a page, and you can see that it's got a bunch of stuff in it. It's got records or tuples, and they're stored in part of the page. And then we've got some kind of directory, which flickering. I hope it's not that data projector. Anyway, a directory down the bottom here, and R6 will give us information about R6, like where is it located in the page. Maybe it tells us how long it is as well, and maybe some other information. Like there might be flags that say whether it's been deleted or not. In any case, so that's what structure of a page looks like. What we're interested in is how do we convert these records into tuples. So clearly these records byte sequences stored, located somewhere in the page, and they represent tuples. We need to extract that information. So the information for a tuple, so there's two ideas that are kind of similar, tuple and record. So a record is basically just a sequence of bytes. So there's a chunk of data in a page. That's what we actually see, that's what we fetch in. So eventually we have to interpret it. So we need to know what's the structure, and clearly the structure, of course, is given in the schema. And as we saw, the schema information is stored in the catalogue. And there was an exercise for you to extract the schema information, including the names of each attribute and the type of the attribute. So all of that information is available in the catalogue. So that's what we see in the page. That's how we want to interpret it. So some of these bytes are interpreted as integers, some are interpreted as strings, and so on. Right, so what do we do with records / tuples? Well, one thing we can do is we can fetch a record given its record ID. And a record ID, as we've seen already, involves information about the relation that the tuple comes from, which page in the file it's stored in, and which tuple it is within that page. So given that information, we can extract the relation information in the page number, and we saw how we can take the relation ID and we can convert it to a file, and then we can use the page number to offset into that file, and so on. So once we've got a buffer full of information, we can then extract a particular record. So we give the record ID or the record number, and it goes to the directory, and that takes us to the appropriate location within the file. So we can get that chunk of binary data, but eventually what we want to do, we want to interpret it as a real database tuple. So it consists of fields of various types. And once we've got a tuple, we need a way of accessing the individual components. Other operations, so I just had get record, to get a record given a record ID. You might say, how did we get the record ID in the first place? Maybe we got it because we had an index file, and the index file stored a bunch of key record ID pairs. So we find an appropriate entry in the index file, and then we want to get the appropriate, the record corresponding to that entry. Right, other things we might do, we might want to modify a record in place conceptually. However, we know that Postgres doesn't modify records in place. In fact, it has to leave the old version of the record because there may be some transaction that's currently using that information. And so it doesn't actually change the record that's identified by this. What we actually do is we make a copy of the record with the new data, and we flag the old copy of the record as having been deleted. So it's kind of like a delete insert thing that happens with Postgres. But I'm sure there are other databases that actually do modify the record in place. Inserting a record, basically we've got to find an appropriate page, or here we assume that we've already identified the page that we want to insert the tuple into, and then this function will do it, and it will tell us whereabouts or in the page that the record occurs, and of course, since we're talking about a record ID, it's also got the page number and the relation ID, and delete a record. So once again, in Postgres, it doesn't actually remove the tuple, it just marks it as not, or as having been deleted by a particular transaction. So any transactions that come along later shouldn't be able to see the tuple. Alright, so once we've got this chunk of binary data ready, we need to be able to interpret it. So we saw the make tuple relation before, so basically it takes this chunk of data and wraps it up in a way that we can then interpret it as a tuple. So once we've got this tuple object, we can then start extracting the individual fields. So we imagine, and by the way, this is not Postgres stuff, this is just generic. Every database will support some kind of functionality like this. So we've got this tuple data object, we want a particular field out of it, we need to know what type that field is. So if it happens to be an integer field, the first field in the tuple, then we might call a function like that, which will give us back an integer value. Similarly, if one of the fields, say the second one is a string, we've got our tuple, we can extract the byte sequence null terminated for that particular field. So all of this kind of stuff will be happening in memory. So, and in fact, the whole page is in memory because it's sitting in the buffer pool. But more than likely, we won't be just dealing with the data sitting in the page buffer. We'll actually make a copy into a local area where we're going to manipulate the tuple. And similarly, if you want to set the value of a field, setting a string field is problematic because it might be a different size, but actually setting the value of an integer, sure, we can do that. Alright, so that's manipulating a tuple once we've got one. Where do we get them? Well, we get them by virtue of access method. So we start running a query, and the query says, I want to get this page because I know there's some useful tuples on it, because maybe we're doing hashing, and we fetch in the page, and then what we need to do is actually get that tuple data. So one possibility, like I said before, if we've got an index file, then the index file will probably consist of a bunch of key record ID pairs. So our query will scan looking for the appropriate key. If we find an entry for that key, or maybe more than one entry, we've then got a record ID corresponding to that key, and then we can call this getTuple function to grab that record for us and convert it to a tuple. Similarly, if we've already got a page loaded and we know that we want a particular record from that page, then we can use a function like this. So a lot of the time you'll see that I write stuff like for each tuple in the page. Basically that's the function that's going to be used to get a tuple from the buffer that represents the page. Right, so when we're scanning a relation, we have some kind of iterator. I already talked about scanning iterators a little bit before, but basically, if we want to start scanning a relation, we need to know which relation we're scanning. We can set up a data structure to manage that, which is going to contain things like what's the current page, what's the current tuple in the page, and so on. If we're doing a scan that involves filtering, then we might actually have the filtering information also stored in the scan object. So clearly it has to hold information that tells us how far we've gone through the scan. And of course, once you start a scan, you typically want to get next tuple, next tuple, next tuple, next tuple. So there's going to be a next tuple function, which goes to the appropriate page, goes to the appropriate record number, the current record, fetches the record data and turns it into a tuple. And of course eventually you're going to run out of data, so you'll want to have some way of indicating that. So there's the typical strategy for scanning a relation. So this basically is doing for all tuples in the relation MyDB. In the relation employee from the database MyDB. And here we're not putting any where clause, but if we did, then we'd add some kind of filtering structure as part of the start scan. I think I left option to possibly have more arguments to the start scan function. Alright, so getting back to records and interpreting them as tuples. Alright, so if we've got a record that consists entirely of fixed length attributes, then we don't actually need to store any information in the record to determine where the attributes are or what type they are. All of that information is going to be the same for every tuple in this relation, and so we can store it once and we can store it as part of the metadata for the relation. So somewhere in the catalogue data we might have some information like this that tells us the first attribute occurs at offset 0 in the byte sequence that makes up the record. The second attribute starts at byte offset 4, third attribute starts at byte offset 24, last attribute starts off at byte offset 34, and the final thing that we might store is the total length of each record in this table. Remember, all the attributes are fixed size, so these are going to be relevant for every tuple in the table. Now, if we're scanning through a table like that, then clearly we're going to make frequent reference to that because we want to grab the next tuple and we need to interpret that tuple. So we'll need this information to be available for every tuple that we have, so clearly we want to cache that somewhere in memory. So the information about where the attributes are in the record. So that's fixed length records are reasonably straightforward, and we can store the information about the attributes once as part of the relation metadata. For variable length records, we have a slightly different issue because each record obviously is going to be different. That's why they're called variable length records. So we need to store information about the attributes within the record itself. And there's a number of different ways that you could imagine that you might structure the record. One way might be to store the length of an attribute at the start of that attribute, and then you say, all right, if I want this attribute number 1, I can grab 4 bytes. If I need attribute number 2, well, I'll skip over these 4 bytes, and I know that the next attribute is 10 bytes long, so I can grab it from there. And similarly, you know, if you need the other attributes, you can work out where they are. Another possibility might be to have some kind of delimiter. So if you need to get the value of the third attribute, you can scan through here until you see that delimiter and say, okay, that's the end of the first attribute. Scan a bit further, end of the second attribute, so therefore the third attribute must start there. And another possibility is to actually have a header for each tuple, which gives you the structure of the tuple. So how many, now this number here doesn't actually need to be in the tuple because we know that every tuple in this table is going to have 4 attributes because that's defined in the schema. But all of this other information would be useful in a header. So we need to know how long the tuple is overall, and then knowing whereabouts the attributes start in the tuple is useful to know. And how do we know how long they are? Well, we can look at the difference between the adjacent attribute offsets to work that out. So this would be the more common kind of strategy for storing information, although without evaluating them. Alright, so going backwards a little bit, a record is just an array of bytes. And a tuple is a collection of values. Each value has a name, which is the field name. Each value has a type, which is important in allowing us to interpret a chunk of bytes. So in some sense, that's like a struct in C. All of that information comes initially from the catalog and might be stored in a header associated with the tuple. I haven't shown all of that information there, I've just shown the length information, but we might also be interested in knowing the type of each of those attributes. Now, given that the types are going to be the same for each tuple in the relation, we don't need to store the types in the individual tuples, but we'd certainly need to store that type information somewhere. But in theory, you could store it in the tuple if you wanted to waste a bit of space. So for variable length records, we need to store a bit of information in the tuple itself, and we saw those three different strategies. All of them have information stored within the tuple. The length doesn't necessarily need to be stored in the tuple, because we saw last time we got that directory at the start of the page, and that directory tells us where a particular record starts. It could also store how long that record is. So wouldn't necessarily need to have that information stored in the record itself. Right, so databases have a number of data types, and SQL defines at least those types. Those types internally, i.e. in the bytes sequence that represents a tuple, are going to be stored something like this. So a date might be stored as a timestamp. In theory, you can store it as a string, that's how you write it, so maybe you can store it that way. A float might be stored as a floating point value, 4 bytes long, but it might also be stored as an 8-byte double precision number. Similarly, integers could be stored as 32 bits or 64 bits, depending on what the database decides to do. And numbers, so the data type number with a length attached to it could be stored as an array of ints, and similarly a varchar could be stored as an array of bytes. Right, so when we're trying to look at a tuple, as I said, we need to be able to interpret what these bytes look like, and so we'll need somewhere to have a list of field descriptors and give information about how to interpret each of the fields. So it could contain information like that. Certainly it would be useful to know that, how long it is, but also it's very important to know what the type is. So we can imagine that we might have a structure like this to represent the tuple. This isn't what Postgres does. We'll have a look at what Postgres does in a minute. What Postgres does is a lot more complicated. But clearly we need to know how many fields there are in the table. That determines the length of this array. And then and once again, this is abstract because you can't implement it like this in C, because you need to specify how long this component of the struct is. But an array for each field, a description containing information like that, and then the actual byte sequence that we read from the page. And in theory, the fields, if the length isn't actually stored in the tuple, then in theory we could perhaps grab this information and store it in the field descriptor, because we have one field descriptor for each tuple. And then we've got this thing that I've called a record, which is basically just a sequence of bytes. Alright, so what could the data field be? Well, it could be just a byte sequence, or it could be a byte sequence that's got some other stuff inserted into it. So we could get that tuple data totally separate from the record data, and in theory we can have the tuple data sitting there. And I said before that we wouldn't necessarily we wouldn't necessarily use the data from the buffer, but we could. If we've got this tuple object, then we could just have a pointer into the buffer, and that information might be stored at that location in the buffer. Or what we could do, and this technique is used in Postgres, is you define a struct like that, like this, so it looks like a struct, but the size varies. So basically all you're telling Postgres here is that there is some stuff following on from the tuple component, which is really just a header. Okay, so this stuff always exists, and even then we know that there's a variable number of field descriptors, but given the value of n fields, we can work out how long this thing is, and then we'll know where the record data actually starts. So if it was stored in a single chunk, like this, and that ... is meant to mean this stuff is attached to the end there. Another thing here, that's these values, the lengths of the fields that I've got stored here are a little bit redundant, or they're stored twice. So we know that the first field is 4 bytes long here, we know the second field is 10 bytes long, we know the third field is 8 bytes, and so on. So in theory we don't need to store these. And the other numbers here are the offsets within the data section of the record. So whatever the database system you're using, it has to make some decision about what's going to be stored in these headers and what's going to be stored in the tuple. So maybe we don't actually store the lengths in the tuple at all. The question then is, how do you work out what they are? So maybe somewhere along the line they actually need to be stored. And there was a question on the forum about that second lab. Why do we have the size of each attribute being 4 more than you'd expect? And could well be that's the reason, because we need to store this length information at the start of each chunk of data. So Postgres knows that that extra thing is there, but in our schema we didn't have that. We weren't allowing for that extra 4 bytes. Alright, so how does Postgres represent tuples? Well, it has a data type called heap tuple. You can find some of the definitions related to tuples there, but most of the interesting definitions live under that directory. Access has a whole lot of other stuff that's not particularly tuple related, so if you look for files that have got tup in them, you'll find the right things. So we need to be able to build a tuple, and this is basically the thing that I called make tuple before. So you need to have some information about what a tuple looks like, which is what this descriptor is. You need to know what all the values are, and interestingly, if we got a value that's null, we don't actually store anything in the record. We simply set a flag in an array that tells us where the nulls are actually located. So we don't have to come up with some distinguished null value. We can simply have, and basically this null thing is going to be a bit string. If it's a 0, it's not null. So we should be looking for some bytes containing a data value. If it's 1, then we know it's null and we don't have to look for bytes. And also you can change a tuple if you want. So Postgres puts tuples in theory into a contiguous chunk of memory, and there's a header at the start, and we'll have a look at the details of those things. And the data values are also wrapped up in a type called datum. So this is what a tuple looks like. Potentially starts with an OID. I've kind of been implying that every tuple has an OID, but you don't actually have to do that if you're trying to save space. You can not have that field, but certainly you need these fields for the for the MVCC. So this is the one that tells you which command created or deleted the tuple, and this is the two fields that tell you which transaction created or deleted the tuple. Why do we have these different things? Because a single transaction can consist of multiple SQL statements, where effectively a command is one SQL statement. If you delete a tuple, what Postgres actually does, it puts in, if you update a tuple, it puts in a link from the new version of the tuple to, the other way. If you update a tuple, it puts in a link from the old version to the new version, which is what that field there is. Then stores the number of attributes, stores a bunch of flags that describe various properties of the tuple. For example, if the tuple is allowed to have null values, then you have a flag that tells you that. In some tuples, you don't have anything that's, everything's defined as not null, so there wouldn't necessarily be allowed to be null values. This is required because we don't know how long this bitmap is. Certainly we know the number of attributes, and that's going to kind of determine that, but it's useful to know where the actual attribute values start. So this field here tells us how far ahead in the tuple we need to look. Now this thing is actually composed of a whole lot of nested structures, and in fact the values aren't mentioned in the structures at all. They just sort of hang off the end. Once you've got all the header information and the bitmap, then the next part of memory is where the data gets placed. So given that we don't have a name for the data, that's another reason why we need this offset, so we can work out where to start looking for the data. Alright, so there's a whole lot of types related to tuples. So this is the sort of lowest level, which is basically allowing, and this type, this is basically saying, well, this thing could be an unsigned integer, it could be a pointer, it's just a 32-bit quantity, basically. So a datum is a single 32-bit quantity. So the actual data value might be stored here if it's small enough. So 32 bits, you could store an int value. It might be, this thing here might actually be a length value, which tells you how long the actual data is, and that's for things like strings. Or if you've got a giant attribute value, that's going to be stored somewhere else. So this information here will tell you where to go, which file, and what offset in the file the information is actually stored. But each attribute is defined by a datum. Alright, so tuple descriptor. I should have started with the top level. Where are we? I think I was building up to it. Alright. So a tuple itself is called a heap tuple to distinguish it from an index tuple, if you like. So there's really only two kinds of things that are stored in PostgreSQL pages. Tuples are stored in heap pages. Index entries are stored. Let me come back. Yeah, so two different types of tuples, if you like, if you want to treat an index entry as a very simple kind of tuple. So a heap tuple is just a pointer to one of these data structures, and you can see that it contains some useful information like which table this tuple belongs to, and then information which gives you the tuple header and the tuple data, and essentially that's that stuff. Right? So the heap tuple actually has another wrapper around all of this. Alright, so the tuple descriptor is something that's stuck at the start of a tuple, and one thing it contains is the number of attributes. Another thing it contains is effectively an array of descriptions for individual attributes, and all of this stuff actually comes from the PG underscore attribute table. And so grabs a bunch of information directly from the fields in the PG underscore attribute table. Then we've got information about constraints. So all tuples have a type associated with the whole tuple, not just the individual attributes. That's what this is for. But there's also an entry in one of the catalog tables for the type, so that's what we'd store there. Does the tuple have an object ID? And because these things, these tuple descriptors, live in a cache in memory, so it's kind of like the buffer pool. You don't want to keep them if you're not using them, so it has something like a pin count, so you can chuck those tuple descriptors out if they're no longer of interest. Alright, so the tuple itself, so I think, let's see where we had on that previous page. No, it was that tuple descriptor. Alright, so what we actually have in a heap tuple, we have a length thing, we have a pointer to itself. I don't know why we have that. I'm sure it's used somewhere. We have to know which table it came from, and we have to have the data itself. Now the data itself is the values plus a bunch of other information, those, you know, xmin, xmax, cmin, cmax, and so on. So those kind of things are stored in here. We saw a CTID on that diagram of a tuple before, counter of the number of attributes. Notice this is a 16-bit quantity, which means we're clearly limited to 64K attributes. Doesn't sound like much of a limitation to me, but probably having 8 bits where you'd be limited to 256 attributes, maybe they thought that was too much of a limitation. So they've been very generous in allowing that. As I said before, there's a mask that tells us various things about the tuples and that offset. And then we've got the bitmap that tells us whether things are nulls or not. If the info mask says that this kind of tuple doesn't have nulls, then I guess the length of this thing would be 1, because you can't really get rid of that 1 and you just wouldn't use it. And so after that, all of the actual data appears. So the data doesn't have a name in the struct itself, but we allocate a struct, plus we allocate a whole lot of space, and we stick all of the bytes into that extra space beyond the end of the bitmap. So that's essentially what appears in a tuple. And oh yeah, so we had heap tuple fields, I think we had that. So basically That's the transaction xmin, xmax, and the command that inserted or deleted the tuple. So interestingly, we store both of those things, but we only store one of them. And the reason for that will probably become clear when we talk about MVCC later on. Alright, so what kind of operations does Postgres provide on tuples? You give it a tuple descriptor, you give it a byte string, you give it an indication of what fields in the byte string, or in fact what fields aren't in the byte string, by the values stored in here, the bit string, and it'll create a tuple and give you back a heap tuple value. If you want to get an attribute, so remember that I said we have some kind of function to get an integer field, and you give the field number and it would get you the value for the field. Well, it's kind of similar to that, but you've got extra information that you need to provide as well. So heap get attribute will go to a heap tuple and extract the value, the datum value, I think, for one field from that tuple. Is an attribute null? Clearly it's just going to look up the bitmap to work that out. And you can, in theory, modify a tuple, but in practice what we actually end up doing is creating a new tuple. So one thing this could do, take in a tuple, take in a new value for some part of the tuple, and then create a new tuple from that, which will then be inserted into the data page. Right, so that's it for the implementation of tuples. So we've looked at how do we represent a relation as a bunch of files, and there's a layer of abstraction to do that. For a given file, a file is partitioned into blocks, so there's a representation for that, and there's a cache of blocks, which is the buffer pool. Then given a page, we can access the individual tuples within a page, and given a chunk of bytes that represents a tuple, we can interpret that byte string appropriately. Alright, so that's all very nice. Why do we do all that? We do it because we want to have higher levels of the system that can deal with pages if they want, and they can deal with tuples, and they can interpret the tuples and see, you know, there was a select query that said the ID value had to be greater than a certain number. So obviously to make that work, we need to be able to extract the value of the ID field given a tuple, and then we can compute the value of the condition that tells us whether we're interested in that tuple. Alright, so given that we've built all this stuff down below, and we've built the page and tuple management, we can now start actually implementing relational operations. So what kind of operations do we have? Selection, protection, join. They're standard set operations like union and intersection. And other things that we have is we'd have scanning, which is basically a selection. We don't have a condition. Sorting, which is different to any of these. Grouping operation, aggregation operators, and so on. So all of these kind of relational algebra operations need to be implemented. Given a database, you're not going to have just one way of implementing selection. There may be multiple different approaches to doing selection, and you may decide, some of them are obviously going to be determined by the file type. So if you've got a sorted file type, the way you do selection, if you've got a query that involves the sort key, you can do it with a binary search or something like that. So that's one way of doing selection. If you've just got a plain old file that's not sorted and doesn't have an index on it, then the only way you can do selection is by doing a scan, checking each tuple, does it satisfy the condition, and so on. So there's not going to be one way of doing selection. There's going to be multiple ways that depend on the structure of the data. So anyway, we want to look at each variant of each operation and look at how much it's going to cost to do it, and think about when the method is actually going to work, or where it's going to be most effective. Right, just a reminder, we talk about tuples and records. Obviously we just thought that they were slightly different ideas, but they're obviously related. Pages and blocks. Pages are interesting because they're the unit of I/O that we need to deal with. We never fetch a single tuple from the disk. We always fetch a page, and then we have to extract the tuples from that page. And a relation is a collection of files, and each file contains a collection of tuples, so overall we get the tuples for the relation. Alright, so as I was saying before, so we've got the relational algebra operations, and they're modified by what kind of file structure we have underneath in order to make those operations work. So you can imagine a primary key selection on a file which is hashed is going to be done quite differently to a primary key selection on a file that has B-tree index is going to be done in a different way to a file that has no indexing, no hashing, and is just a collection of tuples. Similarly, the kind of join that we can do might be determined by the kind of file structure we've got underneath. So we'll look at query costs, because that's the thing that happens most, I guess, unless you've got a system where you're inserting lots and lots of data, some kind of logging system. And we'll also occasionally look at update costs as well. So this is what we see in SQL. We're selecting from a table according to some condition. What that maps down to at the relational in the DBMS engine is finding a bunch of tuples in the files of that relation that satisfy the condition. How we find them depends how the files are actually set up. Inserting a new tuple into a table basically boils down to getting the bytes of data that represent the tuple, finding an appropriate page and copying those bytes into the page, and then making sure that page makes its way back to the file. And deletion, well, basically deletion and update are essentially like selection, except they do things once they find the relevant tuple. Alright, that's a good place to stop, have a break, so I'll resume again after that.